Welcome to the Innovation Series, where I take you on a journey to build complex technology from scratch, step by step, from idea to reality. The main topic of this video is about verification. We'll discuss the essential steps after the external expert submits their delivery. I'll demonstrate how I verify the catapult design submitted by the expert. So far, we have completed two phases, the conception phase and the implementation phase. The final output of the conception phase is the contract requirement. As for the implementation phase, the final output is the actual product and the documentation about the specification of the product. Given the current level of complexity, we can consider the 3D STL digital file as the product documentation, as it defines the specification of the product. Viewing the STL file provides a visual representation of the product. Once it is 3D printed, we will have the actual tangible product in our hand. Since we now have both the product documentation and the physical product, we can consider the implementation phase complete and move on to the next phase. After completing the implementation process, the next step is the verification and validation phase. Sometimes it is abbreviated as VNV. This phase involves testing to ensure that the implementation phase aligns with the conception phase's expectations. VNV consists of two main processes: validation and verification. Validation process assesses whether the device fulfills its intended use. In our case, we will validate the primary concept, which defines the device's intended use. The first sentence of the primary concept states that the catapult is designed to throw a projectile. We will test whether the expert-designed catapult can successfully perform this function. Verification process ensures that the device meets the specified requirements. We will verify the catapult against the contract requirements, which currently include 8 items. We will test whether the expert-designed catapult can successfully perform all the requirements listed in the contract. Let's do a real demonstration, and I'll share my experience after the expert submits the delivery. He provided me with 2 designs, both in STL 3D print format. After opening the files, I found the designs too simplistic and questioned whether they truly implemented my catapult concept. To determine if they meet the intended requirements, I need to perform verification and validation on both designs. For validation, I will test whether each device can successfully throw a projectile. As for verification, I will check if each design meets all individual contract requirements. Now, I'll demonstrate how I validated these 2 designs. The first time I tested the device, I noticed that the projectile container was small, so I had to choose a projectile that would fit. I selected a crumpled paper ball. As long as it could launch the paper ball, I considered it sufficient because I knew this was just designed for a tiny toy. I demonstrated here. Design 1 is on the left and Design 2 is on the right. Both successfully launched the crumpled paper ball, meeting the validation acceptance criterion, the ability to throw a projectile. With this evidence, I had to acknowledge that the expert's design fulfilled the device's intended use. What about verification? If both devices fail to meet the requirements, I can dispute the design and request changes. However, if even one device meets all requirements, I have no grounds for dispute. In that case, the expert has fulfilled the agreement, and modifications beyond the original scope are not an option. Now, let's go through the verification process step by step. First, Requirement 1, or R1. The catapult shall provide the user with the ability to transfer mechanical energy to the catapult. The first design on the left, I could pull it using my thumb. The second design on the right, I could press it using my index finger. Since both designs allow the user to transfer mechanical energy, they satisfy requirement 1 or R1. Second, requirement 2 or R2. As long as the user transfers mechanical energy to the catapult shall store energy. In the first design on the left, I can feel the spring being charged as I push. In the second design on the right, the rod flexes, tenses, and is ready to rebound when pressed. Since both designs store energy while being pushed, they satisfy requirement 2, R2. Next, I verify requirement 3 or R3 and requirement 4 or R4 together. R3, as long as the catapult is storing energy, it shall detect the projectile container reaches a ready position. R4, as soon as the projectile container is in a ready position, the catapult shall lock its position. In the first design on the left, after pulling it to maximum stored energy, I noticed that nothing snapped to hold the container in place. If I released my thumb, the energy would be discharged without the container being locked. This means that the first design on the left fails to meet R3 and R4. In the second design on the right, after pressing it to the maximum, I heard a click. Something snapped onto the rod. When I released my finger, the container remained locked in place. This confirms that the second design satisfies R3 and R4. Let's pause for a moment to consider the impact of these verification results. The design on the left failed to meet R3 and R4, meaning it does not align with our concept. Even a single failure in verification signifies non-conformance, making further testing unnecessary, as verification consumes valuable resources. Moving forward, I will exclude the first design from further verification and focus solely on the second design to confirm that it fully satisfies our concept. Next, I verify requirement 5 or R5 and requirement 6 or R6. R5, the catapult shall provide the user with the ability to load the projectile. R6, as soon as the user loads the projectile, the catapult shall hold the projectile. I noticed that the projectile container was much smaller than I expected. However, I was still able to load a small crumpled paper ball, and the catapult held it securely. This confirms that the design satisfies R5 and R6. Let's continue verifying requirement 7 or R7 and requirement 8 or R8. The requirement 7 says, the catapult shall provide the user with the ability to trigger the release. The requirement 8 says, as soon as the user triggers the release, the catapult shall push the projectile. I realize that there is a small knob here. When I shifted it, the catapult released, launching the crumpled paper ball into the air. So this design satisfies R7 and R8. In conclusion, there were two catapult designs. The first design failed to meet my requirements, while the second design successfully fulfilled all of them. By the success of the second design, this means the expert delivered the product in accordance with the contract. As a result, I must acknowledge that the expert has met the agreement. Since the contract has been satisfied, the expert is entitled to payment, and I have no reason to delay it. Congratulations! Now you have the tangible working product that satisfies your concept. You have just finished your first iteration of the design cycle. Your design cycle began with the primary concept and ended with a tangible product. With the full demonstration of the first design cycle, I'll wrap up our innovation series here. You now have the knowledge to start innovating in any area that interests you, not just limited to the catapult development. You can apply the same process in the design cycle to develop other complex technologies. Good luck in your innovation journey, and I look forward to seeing you in the next series. We have completed the lesson, but our journey is far from over. Although the current prototype meets all the requirements in the contract, it still doesn't align with my expectations. The first issue is that the catapult cannot accommodate larger projectiles. The second issue is that when the catapult launches the crumpled paper ball, it only travels a short distance, whereas I expected it to fly a longer distance. In other words, the prototype lacks the power needed to effectively launch the projectile. The issue cannot be attributed to the engineer or the expert, as they built the prototype based on the specified requirements. The problem lies in the fact that the current design technique does not account for the quality and the constraint. To make the catapult shoot farther or accommodate larger projectiles, these factors need to be explicitly stated in the requirements. This raises a crucial question. What is the systemic approach to incorporating these changes? Should they be included in the primary concept, the activity chain, or directly in the contract? Furthermore, what formula or framework should be used to address these adjustments? These questions will be the focus of the next innovative series. While this series has concentrated on understanding the design cycle until we obtain the first prototype, the next series will focus on improving that prototype by adding design constraints and quality requirements. These constraints allow us to define the limits or performance expectations for the catapult's functionality. As we did in this series, I'll share the formulas for creating design constraints and show how to systematically incorporate them into the documentation tables that connect to the requirements. We will then reach out to the engineer again to build according to the updated requirements. I will also share the story of the 3D printed output they provide and the challenges I encounter during this next iteration. I can't wait to have you join me on the next innovative series. See you there.